Welcome back, everyone. This is EC Fundamentals 1, and starting from this video, we will start focusing on systematic analysis techniques for solving linear circuits. I emphasize here the systematic analysis techniques because we already know some of the techniques to solve a circuit. For example, we do know KCL and we do know KVL, but we've actually never learned how do we systematically apply them in a circuit. We know the concept, in other words, but we don't know the methodology well enough to get useful results in a meaningful way. So nodal analysis will be our first technique, and nodal analysis, as you will see in this video, is basically nothing else but KCL, except that it's KCL applied in a very systematic way. So first of all, let's look at the circuit example so you get an idea of what we mean by applying nodal analysis. If you look at this circuit, it's a fairly complicated schematic, but the main thing that we could be trying to do in a situation like this is to find some unknown currents. For example, you might be interested in finding current Ix, or you may be interested in finding current Iy or Iz. So let's say that these are the unknown currents that we have, and if you were to pay close attention here, you will find out that it's actually relatively easy to find the unknown currents, primarily because those currents are coming out of essential nodes or flowing into essential nodes where everything else is basically known. For example, let's focus on the essential node right here that connects 4 branches. If I apply KCL in this branch, I will have that negative 20, which is coming from this current source right here. It's an incoming current, so I take it as negative. Plus 5, which is this current here that goes downwards. Plus Ix, which is the unknown current that flows out of the node. Plus 4 is equal to 0. 4 is the current that goes through R8 up from that node. So this is a very simple equation. It basically allows you to find Ix immediately, and therefore the job is rather easy. And honestly, if you repeat that process for the other essential nodes, you will get every other current that you need. For example, if you focus on this essential node here, with the red color, you will have now Ix, 4 amps and 15 amps, and essentially you'll be able to find Ix again. And similarly, you can keep marching down the circuit until you find all of the Iy and Iz. You might say, good enough, easy. What if I change the picture now to this one? This is an identical circuit, except that now I haven't given you any of the other currents. I'm only putting down the unknown currents that you need to find. The problem now is that you really don't have such an easy job. You still have a tool to apply. That tool is called KCL, and you can still go to this node, for example, and say, well, now I'm going to apply KCL here, trying to find Ix. But in order to do that, you will have to make an assumption for the current that flows through the R1 resistor. So let's say that I'm calling this current IR1. And you'll have to make an assumption for the current that flows upwards through the R8 resistor. So let's call this thing IR8 and write KCL. Well, if I do that and write KCL again, as I did in my previous case, I will have that negative 20 plus IR1, now this is unknown, plus Ix, which is the current I really want to find, plus IR8, this is unknown as well, must be equal to 0. Now the job is not nearly as easy because I have to first be able to find the currents IR1 and IR8 before I find my current Ix. Well, you might say, okay, I know how to do that. I'm going to go to this node here, and now IR8 will be my unknown current. But then if you pay attention to that node, you will need to account for the current that goes through R3, and you'll need to account for the current that goes through R5, and those are unknown also. Not to mention that you still have the current Iy, and all of these currents are essentially part of what's happening at this essential node. So, of course, you can do that, but you will have to be guessing all the time what's the next step? What are the unknown currents I have to assume? And do I duplicate an equation? And if I write it, for example, for this node, do I duplicate it? Maybe this is the same equation as I write it for this node. As you can imagine, there is a lot of unnecessary, if I mention it, creativity here, which will take a lot of energy and at the end of the day will actually yield to nothing useful. Nodal analysis is exactly the solution to the problem here. In nodal analysis, we will say the following. Instead of directly finding out the currents that you need in a circuit, or voltages, or powers, or anything else that you may need, now I'm going to go ahead and first find all nodal voltages in a circuit. So in other words, regardless of what somebody is asking me to find, it could be power, it could be a voltage drop, it could be current, my technique will first calculate the nodal voltages in a circuit. So the first thing I have to do is I have to define all the nodes in a circuit and ask the question, do I know the voltage at that node? If I do, for example, I know for the ground, here I write it down, 0 volts. If I don't, I will give it a name and consider it an unknown. For example, the node here has a name V1, the node here has a name V2, and so on and so forth. So the first step in nodal analysis is to name the unknown nodal voltages. So it can be done very simply. You literally scan the circuit, you inspect it, and you find out the nodal voltages. In this case, I have 5 unknown nodal voltages all the way from V1 to V5. Now, let's take a pause for a minute, and we will go ahead and find what these nodal voltages are, but let's say that we did know them. So let's say we've performed nodal analysis correctly. What's the next step? Well, once you do know the nodal voltages in a circuit, the currents, the powers, any voltage drops that you want to find will reveal themselves immediately. For example, in this case, let's say I want to find the current Ix. So the current Ix will be equal, according to Ohm's law, to the voltage drop across the resistor R2, which is V1 minus V2, divided by the resistance itself, which is R2. So exactly by applying Ohm's law in this resistor R2, and by knowing the nodal voltages V1 and V2, I can go ahead and calculate Ix. Similarly, if somebody said, calculate how much power does this resistor here, R8, consume, I can still go ahead and find it. Why? Because the power that the resistance R8 will consume will be equal to the voltage drop across the resistance R8, which will be V1 minus V3 square, divided by the resistance itself, R8. So let me repeat this once again. Regardless of the question in the problem, regardless of what your true unknown is, and regardless of what you really want to solve, the first thing that you do is you will calculate the nodal voltages in a circuit, and once you have them, you will apply the right equation to express the unknown quantity with respect to these nodal voltages. All right, now let's go back to the question, how do I find these nodal voltages? Well, the way we find these nodal voltages is by applying KCL at every single node. So this is the winning equation, and we will go ahead and apply KCL. In addition to KCL, though, we will apply Ohm's law. And as you will see, we need both of them in order to apply KCL and express at the end of the day everything with regards to the nodal voltage. Let's go ahead and do this thing step by step. So let's focus first on the essential node 1. So for node 1, if I want to find out KCL, I would say that all the currents leaving this node must add up to 0. Since we're just starting nodal analysis, I will go ahead and show you this graphically, but later on you will have to do this by inspection. So by graphically, I mean I'm going to mark down all the currents. Here are all the currents that are leaving the node. And I will go ahead and write the equation. So I will have negative IS1 this is the current leaving the node from the west, plus IR1, which I will now replace with Ohm's law. So let's do that. The current that leaves that node through R1 is V1 minus 0 divided by R1. Why is V1 minus 0? V1 is the voltage drop, is the voltage of node 1. 0 is the voltage at the ground. And I'm trying to calculate this current. This current will be flowing in the passive sign convention. It starts from V1, it goes towards to the ground, so it is V1 minus 0 divided by R1. Moving on, the current that goes to the east is IX. So normally you're probably used in writing IX, as I said before. But no, as I said before, our goal first is to find all nodal voltages. So instead of writing IX, I'm going to write the current that flows through this resistor R2 as V1 minus V2 divided by R2. That's really exactly, again, Ohm's law on this resistance R2. The current starts from the node V1. It goes into the node V2. So the current is V1 minus V2 divided by R2. And finally, they have the current that flows through the north, through the resistance R8. That will be equal to V1 minus V3, the other side of R8, divided by R8, and the result will be 0. So let's very briefly review what I did here. I focused on node 1, and then I applied what I know, which is KCL, but every time I knew that I had to deal with the current that flows through the resistance, I applied Ohm's law for that resistance, such that I didn't have to deal with the current itself, but rather I could replace this current with a voltage that I need to find, and then unknown voltages are V1 through V5. If you focus on this equation, and if you want to check I've done everything correctly, that equation should only include the voltages, the nodal voltages, as the unknowns. In this case is V1, here's V1 again, here's V2, V1 again, and V3. So it should either do that, or everything else should be known. And IS1 is considered known, R1, R2, and R8 are considered known. Now I'm done with node 1, so let me go ahead now and focus on node 2. So I'm going to get rid of my markings here for node 1, and I'm going to focus now my attention on node 2, which I will put it with the blue color. So let's basically now repeat the process for node 2. KCL says that all the currents leaving that node must add up to 0. So I'm going to mark with blue color all the currents leaving this node. Here are the three colors, the three currents leaving the node. And therefore, I'm going to write it as, you might be inspired to write negative Ix or be tempted to write negative Ix. But again, I would like to stop you and say, no, you're not expressing things with respect to currents. All currents must be written with respect to the unknown nodal voltages. So instead of writing negative Ix, I will write V2 minus V1 divided by R2. This is the current written in the passive sign convention leaving from node V2 going towards V1 through the resistance R2. Now I have the current that leaves towards the south, which is now the current from the source IS2. So it is plus IS2. And finally is the current through the resistor R3. So this will be equal to V2 minus the voltage here. You might say, well, I don't know the voltage there. Of course you do. Look at this short circuit. This voltage is exactly V3. So this will be V2 minus V3 divided by R3. And this, of course, should add up to 0. So let's once again review node 2. I'm adding the current going to the left, V2 minus V1 divided by R2. I'm adding the current going to the south. This is IS2. It's a current source. And finally, I have V2 minus V3 divided by R3. That's the third and final current going to the east. Now, if you're looking at this thing for the very first time, there are probably going to be some questions in your mind which I would rather address here now than later. You might say, 1 second, when you talked about node 1, you marked the currents leaving the node like this. So that meant that you assumed that you had the current that goes from V1 to V2. This is the red current right here. But now that when you shift your attention to node V2, you're marking the same current as going now the opposite direction. So which of the two is happening? Well, the short answer is that when I am applying KCL and I'm saying that the total amount of current leaving the node is equal to 0, I really do not know the true direction of any current. For each node, I can assume that the direction is always outside of the node, knowing very well that that's not always true. But my balance sheet always works. It is totally correct that when you focus on a single node, the total amount of current leaving that node must add up to 0. Of course, if you knew the true direction of the current, you could have actually put it in the circuit and write it down explicitly, like I did in my previous slide right here. When I knew the true direction of my current, I put it 5 amps and 4 amps. And in fact, if you write KCL now for this node, it will work fine. But when you don't know the direction of the current, the best thing you can do is try to balance your budget, your current budget. Think about it in a different way. Let's say you're calculating your financial responsibilities between two different countries. If you're doing that and you're basically trying to balance things for country A, you will take everything that comes into this country as positive, here's your income, and everything that leaves the country as negative. When you count things for country B, you will do the same thing. Everything that comes in will be the income, everything that leaves out will be expenses. And you will say the total amount of my expenses have to be equal to 0, counting as real expenses positive and income as negative. What if there is a trade between these countries? So let's say that country A exports something to country B. Well, as far as country A is concerned, this might count as an expense or income. As far as country B is concerned, it will be the opposite. Because if I'm buying something from country A, I'm spending money from country B, but if I'm buying something from country A is receiving money. It doesn't matter. Each country can do its own balance sheet and say that my total expenses must add up to 0. This is exactly what we're doing for nodes. We're taking each node independently and we're writing down that each node must have current that add up to 0. These are totally correct equations, and therefore you can go and write all of them and basically get the answer. I'm not going to write down here node 3, node 4, or node 5. But I would encourage you very strongly to write those equations down and then go in our textbook and find out if you wrote these things correctly. It will be a great exercise, and you will be getting a ton of influence, a ton of confidence rather, that you're doing things correctly. So I'm going to conclude this video here. I hope you got a good first idea of what the technique is all about. I hope you will be able to apply this technique to several circuits, including the one that we did here. And with that, I want to thank you for watching this video. We will see you next time.